Imagine trying to remember the complex numerical IP addresses of every website you visit. It would be nearly impossible. That's where DNS comes in. DNS stands for Domain Name System. Think of it as the Internet's phone book. It translates human-readable website names like google.com, into the numerical IP addresses that computers understand. Without DNS, we'd be stuck navigating the web using a series of numbers, much like remembering phone numbers for every contact. DNS simplifies this process, making the Internet accessible and user-friendly. It's a crucial part of the Internet's infrastructure, working behind the scenes to connect you to the websites you love. Before DNS, a single file called hosts was used to map host names to IP addresses. This file was maintained by Stanford Research Institute, SRI, and distributed from a single server. As the Internet grew, this method proved unsustainable. In 1983, Paul Mockapetris developed DNS as a scalable solution, revolutionizing the way we interact with the Internet. Today, DNS is an essential part of our online experience, seamlessly connecting us to a world of information with a simple click. Let's break down the key players in the DNS process. First, we have domain names, the human-friendly names we use to access websites like google.com or wikipedia.org. These names are easier to remember than their numerical counterparts. IP addresses are unique sets of numbers that identify devices connected to the Internet. They act like a home address for websites, allowing computers to locate and communicate with them. However, remembering a string of numbers for every website would be a nightmare. That's where DNS resolvers come in. These are specialized servers that act like librarians. When you type in a domain name, your computer contacts a DNS resolver. The resolver then queries different DNS servers to find the corresponding IP address. The DNS system is hierarchical, starting with root servers. These servers are located around the world and direct resolvers to the appropriate top-level domain. TLD servers handle specific domain extensions like .com, .org, or .net. Finally, we have authoritative names. These servers hold the actual DNS records that map domain names to IP addresses. Think of them as the ultimate source of truth for a specific domain. Let's visualize how DNS works. DNS, or Domain Name System, is like the phone book of the Internet. It translates human-friendly domain names into IP addresses that computers use to identify each other on the network. When you type a URL into your browser, a fascinating process begins behind the scenes. 1. Requesting a website. You type www.example.com into your web browser and hit enter. This simple action sets off a chain of events to find the IP address associated with that domain. 2. Checking the cache. Your computer first checks its own cache, a temporary storage of recently accessed websites, to see if it already knows the IP address for www.example.com. This step helps speed up the process if the information is already available locally. If it has the IP address, it will return it to your computer. If it doesn't have the IP address, it starts by querying one of the root servers. These are the top-level servers in the DNS hierarchy. The root server doesn't know the IP address for www.example.com, but knows which TLD server is responsible for .com domains. It provides the resolver with the address of the TLD server. It directs the resolver to the .com TLD server. This server has the final say on the IP address. 6. Finding the IP address. The resolver queries the authoritative name server for example.com and finally receives the correct IP address. This is the address your computer needs to connect to the website. 7. Caching and delivery. The resolver sends the IP address back to your computer, caching it for future use. This means the next time you visit the same website, the process will be much faster. Your computer then uses this IP address to connect to the web server hosting www.example.com, and the website loads in your browser. This entire process happens in just milliseconds, making the Internet feel instantaneous. Section 4. Beyond the address, different types of DNS records. In this section, we will explore the various types of DNS records that play crucial roles in the functioning of the Internet. DNS records are like instructions stored on name servers. They are essential for translating human-friendly domain names into IP addresses that computers use to identify each other on the network. They provide different types of information about a domain, ensuring that various services like websites, emails, and other internet-based applications function correctly. Here are some common DNS record types that you should be familiar with. A record, the most common type, maps a domain name to its IPv4 address. For example, connecting www.example.com to 192.168.1. This is fundamental for directing traffic to the correct server. ATA record, similar to A records, but maps a domain name to its IPv6 address, the newer, longer IP address format. This is increasingly important as the world transitions to IPv6. CNAME record stands for canonical name and creates an alias for an existing domain name. For example, pointing blog.example.com to www.example.com, this helps in managing multiple services under a single domain. MX record specifies the mail server responsible for handling email for a domain. For example, directing emails sent to example.com to the correct server. This ensures that emails are delivered to the right destination. TXT record allows you to store text-based information, often used for email security settings like SPF, Sender Policy Framework, and DKIM, domain keys identified mail. These records help in verifying the authenticity of the emails sent from your domain. NS record specifies the authoritative name servers for a domain, indicating which servers are responsible for providing DNS information. This is crucial for the proper resolution of your domain. PTR record, a reverse DNS record that maps an IP address back to a domain name, often used for email server verification. This helps in confirming that the IP address is associated with a specific domain, adding an extra layer of security. Section 5. When DNS goes wrong, security threats and solutions. While DNS, or domain name system, is crucial for the functionality of the internet, it's not immune to various security threats that can compromise its integrity and reliability. Hackers and cybercriminals can exploit vulnerabilities in DNS to redirect unsuspecting users to malicious websites or disrupt access to legitimate ones, causing significant harm. One common attack is DNS spoofing, also known as DNS cache poisoning, where attackers intercept DNS requests and provide false IP addresses, leading users to harmful sites. This malicious redirection can lead users to fake websites designed to steal sensitive information, such as login credentials, personal data, or even distribute malware to their devices. Another significant threat is DDoS attacks, or distributed denial of service attacks, where attackers flood DNS servers with an overwhelming amount of traffic, rendering them unable to respond to legitimate user requests. DNS tunneling is another sophisticated technique used by attackers. It involves sneaking malicious traffic through DNS requests, effectively bypassing traditional security measures and firewalls. This method can be used for data exfiltration, allowing attackers to steal sensitive data or to establish covert communication channels for ongoing malicious activity. Fortunately, there are robust solutions available to mitigate these threats and enhance DNS security. One such solution is DNSSIC, or Domain Name System Security Extensions, which adds a crucial layer of authentication to DNS records, making it significantly more difficult for attackers to spoof DNS responses. Anycast routing is another effective measure. It distributes DNS traffic across multiple servers, reducing the risk of a single point of failure and making it harder for DDoS attacks to succeed. Additionally, rate-limiting techniques can be employed to help mitigate the impact of DDoS attacks by throttling traffic from suspicious sources, ensuring that legitimate traffic can still get through. By implementing these comprehensive security measures, we can significantly strengthen the resilience of the DNS system, ensuring it remains robust and capable of protecting users from a wide range of online threats. Section 6. DNS is the unsung hero of the internet, working silently in the background to connect us to the digital world. It translates complex IP addresses into memorable domain names, making the internet accessible and user-friendly. Without DNS, navigating the web would be a daunting task, requiring us to remember long strings of numbers for every website. From the moment you type a URL into your browser to the instant a web page loads, DNS plays a crucial role in facilitating this seamless online experience. It's a testament to the ingenuity of the internet's design, allowing billions of users to connect and interact with ease. As we rely more and more on the internet for communication, information, and entertainment, the role of DNS becomes even more critical. By understanding how DNS works and supporting efforts to enhance its security, we can ensure a safer and more reliable online experience for everyone.